Good morning. In today's lecture, we'll continue talking about additions of various reagents onto alkene double bond. And we will actually continue with the reaction that we left off with last time, and that will be addition of halogens across the double bond of alkenes. As we've seen previously, this reaction involves alkene acting as a nucleophile and attacking the Br2 molecule, which under the influence of this nucleophile gets polarized, and so one of the bromines, which is the electrophilic one, gets attacked and back attacks the bromine, while the other one simply leaves as Br-. And what results is this three-membered ring with a positive charge known as the bromonium ion, as well as the Br-, which is a side product, but an important side product because it can now act as a nucleophile and open up the bromonium ion to give us the final product in a reaction which is very similar to an SN2 reaction. Basically, a backside attack occurs here. Br plus is a good leaving group, much like H2O plus is in protonated alcohols, and the strain in the three-membered ring assists the reaction because a lot of energy is released after this ring is opened. And so what results is this anti-addition onto the double bond, again consistent with the backside attack. To look at an example of this reaction, we could see we could react this trans-2-butene with bromine, and this will give us a backside attack, but the stereochemistry of an alkene will be preserved in this conformation of the dibromo alkene. And if you look at this in Fischer projection, we could see that this is indeed a meso compound, so achiral. But the point is that these reactions are stereospecific, and they occur with very precise stereochemical control. Okay. Now, the same reaction will work with chlorine. If we try reacting propene with chlorine, the first step of the reaction will again involve the same mechanism and will give us a chloronium ion now. And of course it will give us Cl-. And Cl- can indeed come back and open up this this three-membered ring to give us the final product. But if we consider here for just a moment the role of Cl-, we realize it's a nucleophile, and there is really no reason why Cl- should be the only nucleophile that can do this function, open up the three-membered ring. Indeed, because three-membered ring is so strained and it has a good leaving group, this positively charged halogen, even weaker nucleophiles should work just fine. And indeed, this is an effect that we see when we perform this reaction in water. Water is used as a solvent in these reactions, and even though it is a weaker nucleophile than Cl- or Br-, its mere concentration is huge because it's used as a solvent. And now water can act as a competing nucleophile and instead of Cl- attacking, we'll get water attacking and open up the chloronium ion to give us, again, a backside attack, inversion of stereochemistry of that one carbon, and overall an anti-product. Which then eliminates the proton to give us this. Now, this works for water, it works for alcohol, it works for acetic acid. Any solvent that is solvent and can be reasonably nucleophilic will work here. This is also an interesting issue because because it highlights the regiochemistry of attack. And it occurs on this more substituted carbon. The reason for that is that we can look at this cation, the chloronium cation, as really a mixture of two resonance structures, if you want to. One which has plus here. Now be careful, this is not actually a chloronium cation, this is just for our rationalization purposes. This could be one resonance structure, and the other resonance structure could be this one, with the positive charges over here. And chloronium cation overall acts more like this resonance structure. These technically are not resonance structures again, but acts more like this structure because this is a secondary cation, so it's a more stable cation. And so this is why water and other nucleophiles will attack here preferentially. Okay? So overall, we're still getting products of formal Markovnikov rule because we still get the most stable intermediate and then derive products from that most stable. To give you just one example of this reaction in a cyclic system, if we have this cyclopentene and react this with Br2 and water, then we will get, again, anti-attack, Br2 and OH minus on different sides. This, because this is symmetric, alkene doesn't really matter which carbon is attacked, so we get both products, in this case, both enantiomers of our product. Again, this is a general phenomenon that the competing nucleophile can compete with Br minus or Cl minus in opening the corresponding bromonium or chloronium ion to give us these products with two different functional groups. And clearly this is synthetically quite interesting because it allows us to introduce two different functional groups into a molecule in the same synthetic step with relatively high level of regiochemical and stereochemical control. So this is a predictable reaction, and in synthesis predictable reactions are good. Next topic, we'll see a little bit different of a reaction, a hydrogenation of alkenes, which is a very commonly used reaction, but it proceeds through a heterogeneous mechanism, which is quite different from the ones we've seen so far.